We'll let y and x be the sine of a and the cosine of a. So we have x squared plus y squared is equal to 1, and we'll substitute into the given equation. Tangent is y over x, and this is equal to 2x, so we'll solve for y. We'll combine these two equations to get this quadratic. We'll use the quadratic formula to solve for y. We are given that a is an acute angle, which means that the sine and cosine are going to be positive. So we'll take the positive value of y here. We can use either of these equations to solve for x. Let's use this one. When we plug in our value of y and simplify, we end up with the square root of 17 minus 1 in our numerator and 2 root 2 in the denominator. We'll let a sub n be equal to this expression. Secant is 1 over cosine, so I'll write this as 1 over x to the n. And this next term is the nth power of y over n. We'll combine these fractions. We want to count the number of a sub n's that have 9 in the units digit. Let's look for a sub n, that's an integer, in order to narrow it down. We'll substitute our values of x and y that we found earlier. Since we're trying to make this fraction into an integer, we need to be able to square out these square root signs. So we're not going to get an integer when n is odd. So let's restrict our search for an even n. We'll set n equal to 2 times m. Using our rules for exponents, we're going to square y and express it as a power of m. So I'll substitute for y, and then we'll raise this to the mth power. Foiling out the numerator, we get 17 plus 1 is 18, minus 2 root 17, and we'll square the denominator. All of these terms are even, so I'll pull out a factor of 2. Let's do the same thing with x. Squaring the numerator gets rid of the square root sign, and our denominator is 8. Let's write our expression now in terms of m. I'll get rid of these denominators in these two fractions, and then we'll rationalize the denominator. I'll distribute this over the two terms in the numerator, and in the denominator we have the difference of squares raised to the mth power. We'll multiply these two factors, and in the denominator we have 17 minus 1, or 16 to the mth power. Here we have 9 root 17 minus root 17 is 8 root 17. And then we have 9 minus 17, which is minus 8. That's great news because now we have a common factor. We'll be able to pull out 8 to the m power from this term, and then we have it in this term as well. So canceling with the denominator leaves us with 2 to the m, and this is our new expression. Again, we're looking for these terms that are integers, so let's expand these binomials. In the numerator, we're taking the sum of these two expanded binomials, and we notice that every other term is going to cancel. So we're going to be left with these powers of root 17 that differ by 2. And in order to get rid of the square root sign, we again need m to be an even number. So let's let m be equal to 2k. We'll rename the terms in this sequence b sub k. And we'll rewrite these in terms of powers of 2k. We'll use our rules of exponents to square these first, and then take them to the kth power. Squaring this first term, we get 17 plus 1 is 18 plus 2 root 17. Here we have 18 minus 2 root 17 to the kth power. These are all even, so we can pull out 2 to the k from the two terms in the numerator and cancel them with the denominator. Let's write b sub k as the sum of two fractions. Let's let r be 9 plus root 17 over 2, and s will be the other fraction that we're raising to the kth power. This simplifies our expression to the sum of the kth powers of r and s. Let's see if we can express these terms, b sub k's, in terms of previous terms in the sequence. If we look at b sub k plus 1, we see that we're multiplying r sub k times r and s to the kth power times s. Let's see what happens when we do that. When we multiply this, we get the terms that we want, r to the k plus 1 and s to the k plus 1. But we also get r times s to the k and r to the k times s. We can factor out r times s from these last two terms, and we get the sum of r and s raised to the k minus 1 power. And this is b sub k minus 1. Let's see if we can find these quantities, the sum of r and s and the product of r and s. The sum is 9. We have the difference of squares again in our numerator, and our numerator is 64. So that means the product is 16. So let's solve for b sub k plus 2 in terms of the previous two terms. And we'll substitute 9 and 16 for the sum and the product of r and s. Now that we found our integers, we want to figure out when these b's are going to have a 9 in the units digit. So we'll substitute our expression here, and we'll simplify it a bit in terms of mod 10. We'll start our sequence at b0. b1 is just the sum of r and s. We already found that. That's 9. And we found our first valid value of n. For b2, we're going to take 9 times the previous value and add 4 times the value that came 2 before that. We only care about the mod 10 residual, so I'll only write down the units digit. 9 times 9 is 81, so I'll just put down a 1. And 2 times 4 is 8. Here's another valid solution. Let's find b3. We'll take 9 times the previous value and 4 times the value that came before it. Writing down just the units digit, we get 7. Keep on going to b sub 4. We'll take 9 times 7 and 4 times 9. We get 3 and a 6, and we get a 9 again. Each term depends on the 2 that came right before it. So when we get 2 9s in a row, we won't need to check anymore. b5 is 9 times 9 and 4 times 7. And in mod 10, that also gives us a 9. We know that the next term is going to be 7 from what we had before. It looks like our valid solutions repeat in groups of 3. 249 is a multiple of 3, so that's going to have a 7 in the units digit. The rest of these numbers are going to be 9. So 2/3 of these numbers, from 1 to 249, are going to have a 9 in the units digit, plus this last one. That's going to give us our answer of 167. If you'd like me to solve any other contest problems, please leave them in the comments.